Solving rational inequalities requires a little bit of knowledge about the graph of the inequality. So take, for example, the graph to the right. Let's say we wanted to find where the graph was greater than 0. Well, if we look at the line where 0 is, we're looking for the positive parts of the graph. So if we look at this graph, we can see that it's positive at this initial stage, stops being positive at the x-intercept, starts being positive again after the vertical asymptote, stops being positive at the next x-intercept, and again starts to be positive after the vertical asymptote. So if I were going to say, okay, where is this graph greater than 0? Well, it is greater than 0 from negative infinity all the way up to that x-intercept, which is negative 5. Now, it doesn't equal 0, so I have to use a parentheses in my interval notation. Starts to be greater than 0 again after the vertical asymptote, so that would be at negative 3. And in this case, there's a hole, and the graph doesn't exist at the hole, so I have to make sure I take that out of my solution set. Still positive right up until that x-intercept. Then it doesn't become positive again until after the vertical asymptote. So the solution set for this one is pretty big, but you can see that there are several intervals where the graph is greater than 0. You can also think about it in terms of the other inequality. So let's say we wanted to find where the graph was less than or equal to 0. Now we're looking for where it's negative. So we can see that it's negative on this part right here, that interval. And it's also negative on this interval. So if we were going to write it, we would say, okay, it starts being negative at the x-intercept. Since it can equal 0, the x-intercept is included. So I would start with a bracket and a negative 5. Then it goes up to that vertical asymptote. Now, after the vertical asymptote, it's positive for a while. It doesn't start to be negative again until the other x-intercept. However, remember there's a hole. So we have to take that out of our solution set. So we have to take out that point of 1. What's nice is that it's not really included in that interval anyways, so we don't really have to consider it. We can start up again at 2, go up to the vertical asymptote, and we're done. So there's less intervals where it's less than or equal to 0, or where it's negative. So think about the points that I was referring to. I talked about the x-intercepts, I talked about the vertical asymptotes, and I talked about the holes. These are all things we need to consider when we're considering an inequality. These things are known as critical points. If you remember graphing or solving quadratic inequalities, we use the critical values there too. In quadratics, our critical values were just the x-intercepts. Here, there's a couple other things we need to consider that affect the behavior of the graph or affect the sign of the graph. Those are the vertical asymptotes and the holes. We're still going to do it in the same way by looking at a number line and putting our critical values on the number line. It's easier to do that way because you don't need to graph the entire thing. You just need to know what the critical values are and try some test points. Now keep in mind we are always going to relate it to 0. So sometimes this involves using some of the other rational solving skills that we had, like multiplying and dividing rationals as well as adding and subtracting rationals, if it's not already set up to be related to 0. So let's look at an example without a graph and see how that works. So here we have the rational x plus 3 over x minus 4, and we want to find where it is less than 0. So what we need to do is find the critical values of this graph. Since it's already related to 0, we don't have to do any work. We can just go ahead and find those things. So the critical values for the critical points are going to be the x-intercepts, the vertical asymptotes, and the holes. Now we don't have any holes in this case because we didn't have to do any work, nothing canceled out. So we're just going to focus on the x-intercept and the vertical asymptote. Looks like the x-intercept was where the numerator equals 0. So in this case, the x-intercept is at the point -3, 0. There's only one vertical asymptote, and in this case, it's where the denominator equals 0. So our vertical asymptote is x equals 4. So we really only have two critical points we need to worry about in this problem. We need to worry about the x-intercept, and we need to worry about the vertical asymptote. So in order to solve this, let's go ahead and draw our number line and put our critical values on the number line. So I have -3 as one critical value, and I have 4 as the other critical value. I'm going to put a circle there to help me remember what symbols to use. So starting at the x-intercept. The graph, it does exist at the x-intercept. However, I don't want to know where it is less than or equal to 0. I want to know where it is strictly less than. So I'm going to keep it an open circle. The graph does not exist at the vertical asymptote, so no matter what the inequality sign is, it's always going to be an open circle. Well now, if I don't want to have to graph the entire thing, I can go ahead and choose a test point in between all these intervals to see which of the intervals represent my solution set. So I'm going to start with a test point of -2. Sorry, not -2, -4. So that means evaluate your function at -4 and see what the sign is. So I have -4 plus 3 over -4 minus 4. Well, that ends up being -1 over -8, which is positive 1/8. Really, I don't care what the value is, I just care that it's positive, and I'm going to mark that on my number line. Now I'm going to choose a test point in between -3 and 4 to find out what happens on this interval. I'm going to choose 0. I usually choose 0 because it's the easiest one to work with. So I have 0 plus 3 over 0 minus 4. I have 3 over -4, which is a negative number, -3/4. So that interval is negative. Now you need to choose something in the last interval, and I'm just going to choose 5. So I'm going to plug in a 5 for all my x's. So I have 5 plus 3 over 5 minus 4, which is 8 over 1, which is a positive number. Now I'm looking for where it is less than 0. And what kind of numbers are less than 0? Negative numbers are. So that's the interval I'm going to use. The interval between -3 and 4. So my solution set are all of the x values in between, or in that interval from -3 to 4. I'm not going to use any brackets because it cannot equal 0. I don't have any closed circles. And that would be my solution. The set of all x's between -3 and 4 is where the graph would be negative, or where it would be below the x-axis. So here we have another rational that's related to 0. It's already factored, so I can go ahead and find my critical values, my critical points. So we know that our critical points are going to be our x-intercepts, our vertical asymptotes, and our holes. Again, there's no holes, so we can not include or not worry about that at this point. The x-intercepts are the numbers that would make the numerator equal to 0. In this case, there isn't an x-intercept either. All I have is a vertical asymptote that I need to worry about. So my vertical asymptote is going to be what makes the denominator equal to 0, which is x equals 2. That is the line where the vertical asymptote exists. So now we can go ahead and sketch this on our number line. Sure, you could graph the whole big thing if you really wanted to. However, when you think about it, we're just going to be looking at that x-axis, and that x-axis is represented by our number line. Then we can use test points, and it usually goes a little faster than graphing everything out. So on my number line, I'm going to go ahead and put my 1 critical value, which is 2. Now, in this case, I can be greater than or equal to 0. However, remember, at a vertical asymptote, the graph does not exist. So even though I have a greater than or equal to sign, I have to keep that an open circle. Now let's choose some test points. I'm going to choose a test point on each side or each interval. So I'm going to start with the test point of 0, because, again, that's the easiest one. 1 over 0 minus 2, which is 1 over negative 2, which is negative 1/2. So this interval is the negative interval. Now if we go on the other side, I'm going to choose 3. So that would be 1 over 3 minus 2, which would be 1 over 1, which is 1, which is a positive number. So this is a positive interval. So now think about your inequality. You want to look for the ones that are greater than or equal to 0. That means positive numbers. So we can see which interval represents our solution set. Our solution set in this case would be the set of all x's from 2 to infinity. Again, I need to use a parentheses because the graph does not exist at that critical value because it's a vertical asymptote. And we're done. Woohoo! So you can see that inequalities really aren't too bad. The trickiest part of solving these inequalities is going to be relating the rationals to 0. So, haha, I have one that's not related to 0. If you were to graph this, you could relate it to the line where y equals 3. However, since we're going to do this without graphing, we're going to need to get it to be less than 0. So I'm going to subtract 3 from both sides. That way I end up with x over x minus 3 is less than 0, which is good. However, I can't figure out any of my critical values from this form. So I'm going to need to change this form around a little bit. I'm going to need to get it into one rational, which means I'm going to have to use my skills from adding and subtracting rationals. So I can see that I have a denominator of x minus 3, and I need that with the other term as well. So that leaves me with x over x minus 3 times x minus 3 over x minus 3 is less than 0. Alright, now we just have to do a little bit of math. We have x minus 3 times x minus 3 over x minus 3 is less than 0. Can do some distribution here. So we're going to end up with x minus 3x plus 9 over x minus 3 is less than 0. Now I'm ready to finish this up. I'm going to go up to the top. I'm going to have negative 2x plus 9 over x minus 3 is less than 0. So we can go ahead and we can graph from this point. You could factor the top a little bit further if you wanted to factor out the negative sign, or you can just leave it as is. If we leave it as is, it's just going to change a little bit in our calculations. It's not really going to do anything too crazy. So now what we can do is go ahead and find our critical values, or our critical points. Remember that your critical points are going to be your x-intercepts, your vertical asymptotes, and your holes. Again, we don't have any holes, so we can ignore that part. We can focus on the other two. The x-intercepts are what's going to make the top equal to 0. So I need to figure out what's going to make negative 2x plus 9 equal 0. Well, now that's just an equation you have to solve. So negative 2x equals negative 9. Divide both sides by negative 2. You get x equals 9 halves. So the x-intercept, or one of my critical points, is going to be 9 halves. Vertical asymptote is what makes the bottom equal 0, and in this case it's x equals 3. So now we're ready to go ahead and draw our number line and put our critical points, or our critical values, on our number line. 9 halves is about 4.5, so that one is going to occur over here, and my 3 will occur on the left. Now I need to be strictly less than 0, so whether I have an x-intercept or a vertical asymptote, I can have an open circle. Now you can see we have 3 distinct intervals, and on each of those intervals we need to choose a test point. I'm going to start with 0, because it's easiest. So we have negative 2 times 0 plus 9 over 0 minus 3, which is 9 over negative 3, which is negative 3. But again, that value doesn't really matter. What I care about is the sign. So I can see that the sign is negative here. Now if we choose something in between, let's say 4. I would have negative 2 times 4 plus 9 over 4 minus 3. Well, that would give me negative 8 plus 9 on the numerator, so that would be 1 over 1. So the value of this one is positive. Now let's go to the other interval, choose something bigger than 4.5, so that would be 5. So I have negative 2 times 5 plus 9 over 5 minus 3. So that would give me negative 10 plus 9, which is negative 1, over 2. So this is a negative interval. Now when we write our answer, when we write our solution set, we're looking for the sets where it is negative. So we're looking for the things less than 0. And when we write out our solution set, I have absolutely no room to do it. I'm going to try to squish it into the bottom. We're going to list all of those intervals. So our solution set is the set of all the x's from negative infinity to 3 and from 9/2 to infinity. Sorry I wrote over stuff, but I didn't want to have to start a whole new slide just for that. So this one added a couple steps. We had to relate it to 0, but once we actually had it related to 0, it didn't change what our work was. We were still looking for critical points and then evaluating test points on those intervals. Yay, this one is related to 0 already. However, it's not factored, so we are going to have to do a little bit of work before we can go ahead and find our critical values, or critical points. So in this case, the numerator will multiply to be negative 2 and adds to be negative 1. So I'm going to end up with x minus 2. I'm going to end up with x plus 1. That's my numerator. The denominator will multiply to be negative 3 and adds to be negative 2. That would be x minus 3 and x plus 1. And I'm relating this all to 0. Well, now I can see that in this one I actually do have a whole at negative 1. So I end up with x minus 2 over x minus 3 is greater than or equal to 0. Remember that whole is going to come into play when we list out our critical values or our critical points. We need our x-intercepts, our vertical asymptotes, and our wholes. What's cool is that you really only care about the x values. It doesn't really matter what the y values are. So for our whole, all we need to worry about is the negative 1. We don't need to worry about what y value it is. We just know that the graph or the set of the answer set is not going to include negative 1. X-intercepts are what's going to make the numerator equal 0, and in this case it's 2. And the vertical asymptote is what makes the denominator equal 0, which in this case is 3. So now that I have all my critical points, I can go ahead and graph them on my number line and consider what circle I would have, or what sort of whether you'd have an open or a closed circle. So make sure you're careful about putting them in order, otherwise you're going to choose weird things on your interval and get all messed up. Negative 1 is a whole, so the graph doesn't exist there no matter what. I'm going to keep that an open circle. 2 is an x-intercept. In this case, I can be equal to the axis, so I'm going to use this as a closed circle colored in. Now our 3 is a vertical asymptote, so that's going to be another open circle. Now we're ready to choose some test points on each interval. So we need to choose something. I'm going to choose negative 2. And evaluate it. You can evaluate it at your easiest one. So that would be negative 2 minus 2 over negative 2 minus 3. Which is negative 4 over negative 5, which is a positive 4/5. So that interval is positive. Then we jump over to the other side, and I'm going to choose 0. So I end up with 0 minus 2 over 0 minus 3, which is negative 2 over negative 3, which again is positive. This is why you can't just assume things go back and forth. Those holes mess you up. Now I need to choose something in between 2 and 3. I'm going to choose 2.5. So that means I have 2.5 minus 2 over 2.5 minus 3, which is 0.5 over negative 0.5, which again, I don't care what the value of it is, I just care about the sign, and that is a negative interval. Last but not least, I'm going to choose something in the last interval, so I'm going to choose 4. So I have 4 minus 2 over 4 minus 3. At this point, you should be able to see what the sign is. If not, go ahead and evaluate it a little bit further. That gives you 2 over 1, which is a positive value. Now, we are looking for the intervals where this graph is positive. So we are looking for this one. We have 3 of them, because positive numbers are greater than 0. So now we can go ahead and list out our solution set, the set of all x's, from negative infinity to negative 1. Again, parentheses, because I can't exist at the hole. The graph starts up again after the hole, and it continues to be positive until it hits that x-intercept. Now, since it's okay for me to exist on the x-axis, this one is a bracket, because the x-intercept actually is a point. Then we start up again after the vertical asymptote, which it does not exist at, so it's a parentheses. And it continues being positive to infinity. So we have our big old solution set right there. Again, it just involves finding the critical values and then evaluating the values of the graph in between those. So here's another one we have to factor before we can actually finish it. It is already related to 0, so we don't need to worry about that part. But in order to find those critical points, we have to have it in factored form. So I'm going to factor the numerator. Looks like we're multiplying to be 2 and adding to be 3. So that would be x plus 1 and x plus 3. And then the denominator is a difference of squares. So I'm going to have x minus 4 and x plus 4. This is all going to be greater than or equal to 0. Now nothing cancels out. So when I list out my critical points, I'm not going to have to worry about any holes. I will have some x-intercepts, and I will have some vertical asymptotes, but no holes. So our x-intercepts, it looks like we're going to have 2 x-intercepts in this case, the numbers that would make either of the numerator factors equal to 0. So that would be negative 1, and that would be negative 3. We also have a couple vertical asymptotes. So we have x equals 4, and we have x equals negative 4. This means we have 4 critical points that we need to worry about. So we just need to go ahead and put those 4 critical points on our number line to figure out which intervals are the ones that are greater than or equal to 0. So be very careful about putting them on in order. Negative 4, negative 3, negative 1, and positive 4. So now we need to determine what circles we're going to use. Negative 4 is a vertical asymptote, so no matter what, it's open. Negative 3 is an x-intercept. Now, again, I can be equal to 0, so this one is going to be a closed circle. Ditto for negative 1. And then our last vertical asymptote is going to be open because the graph doesn't exist there. So we have several intervals that we need to go ahead and pick some test points on. I'm going to start with the first one, negative 5. Now, this is where not really evaluating it will come in handy, because we're going to have negative 5 plus 1 times negative 5 plus 3 over negative 5 minus 4 times negative 5 plus 4. So I'm going to do this one a little bit different. I'm just going to focus on the signs. Negative 5 plus 1 ends up with a negative value. Negative 5 plus 3 is also a negative value. Negative 5 plus 4 is negative. And negative 5 minus 4 is negative. And negative 5 plus 4 is also negative. So I end up with a negative times a negative, which is a positive, over a negative times a negative, which is a positive. So this interval, regardless of what it works out to be, is going to be positive. Now we can choose something in between negative 4 and negative 3. I'm going to choose negative 3.5. And you can do this one the same way. Negative 3.5 plus 1 is going to yield a negative. Negative 3.5 plus 3 is also negative. Over negative 3.5 minus 4, which is negative, times negative 3.5 plus 4, which is positive. So that's going to give me a positive over a negative, which is the negative. So that interval is a negative interval. Now we need to choose something on the next interval, negative 2. I'm going to do this one the same way as well. Okay, negative 2 plus 1 is a negative. Negative 2 plus 3 is a positive. Negative 2 minus 4 is a negative. And negative 2 plus 4 is a positive. So I end up with a negative over a negative, which is a positive. That's a positive interval. Now, we still have 2 more intervals, and I'm totally running out of space. Alright, I can do it. 0. I'm going to do my 0 work down here. So, 0 plus 1, positive. 0 plus 3, positive. 0 minus 4, negative. 0 plus 4, positive. So we end up with a positive over a negative, which is a negative. So we know that interval is negative. And we go to our last interval, and I'm going to choose 5. So again, I'm going to do this the same way. Worry about the signs. 5 plus 1 is positive. 5 plus 3 is also positive. 5 minus 4, positive. And 5 plus 4 is also positive. So we end up with a positive interval here. Now we're looking for the points, or the places, where this is greater than or equal to 0. So that would be all of the positive intervals. We have 3 of them. So our answer is going to be the set of all x's from negative infinity up to that first vertical asymptote at negative 4. Then it's going to start up again between the x-intercepts, and I'm going to use brackets because it can equal these. Then the last interval is going to be from the last vertical asymptote all the way up to infinity. Those are the 3 intervals on which this graph is positive. I wanted to give you guys one more example where you needed to change it around in order to make it related to 0. So this last example I'm going to do will do that. I'm going to start out by going, I kind of like my rationals, the stuff I do, to be on the left. So I'm going to rewrite this one as x plus 6 over x plus 2 is less than or equal to x. I know that that's weird, but I know a lot of you guys like that too. Do you have to do that? No, but that's the way I'm going to do it. Notice how I flipped the entire thing over, so I needed to flip my inequality sign. Now we need to relate it to 0, so we're going to have to get rid of that x by subtracting x from both sides. So you have x plus 6 over x plus 2 minus x is less than or equal to 0. Now we have to get this into one rational, so we're going to need to change things based on the common denominator. In this case, I have a common denominator, or the denominator I need is x plus 2. So I'm going to have x plus 6 over x plus 2 minus x times x plus 2 over x plus 2. That gets me my common denominator. Now we can evaluate this a little bit, or simplify it a little bit. So we end up with x plus 6 minus x times x plus 2 over x plus 2. Up to the top, I will have x plus 6 minus x squared minus 2x over x plus 2. A little bit more work involved. I'm going to rewrite this in standard form and combine like terms. So I have negative x squared minus x plus 6 over x plus 2 is less than or equal to 0. I actually can't find my critical points or my critical values at this point because I need to factor that top a little bit further, or factor that numerator. So I'm going to start by factoring out the negative sign. Alright, now we have a basic trinomial. What multiplies to be negative 6 and adds to be 1. That's something we can factor. Multiplies to be negative 6 and adds to be positive 1. We're going to have x plus 3 and x minus 2 over x plus 2. So this is the thing that we're actually going to look at when we draw our number line and when we find our critical values. Since I'm running out of space, I'm going to go ahead and move to another page, so just give me a second and I will be right back. Alright, as promised, I came right back. I went ahead and rewrote the final rational we were going to use to find our critical points ahead. I went ahead and wrote that up there. It's not any different than it was on the other page. It's just black now instead of, I guess it was red before. Regardless, let's move on. Critical points. X-intercepts, vertical asymptotes, and holes. No holes in this one, so yay, there was at least that silver lining. We do have a couple x-intercepts, and we have a vertical asymptote. So the x-intercepts are what's going to make those factors equal to 0. So we're going to have an x-intercept at negative 3. We're going to have an x-intercept at 2. Then the vertical asymptote is going to be x equals negative 2. Now that we know what these critical points are, we can go ahead and put them on a number line and then evaluate at the intervals. So we have negative 3, negative 2, and 2. Now I need to be less than or equal to 0, so I'm going to start with the negative 3. That is an x-intercept, so it can be included, so it's going to be a closed circle, so I would need a bracket for that one. Then the negative 2 is a vertical asymptote, so no matter what the inequality sign is, not included. And the last one is another x-intercept, so that will be another closed circle. So we have 4 intervals that we need to evaluate our function for. Let's go ahead and start with the one on the left. I'm going to say negative 4. So I'm going to have negative 4 plus 3 times negative 4 minus 2 over negative 4 plus 2. Remember how I used only signs in that other example? I'm going to go back to doing that here too. I have a negative times a negative times another negative over a negative. Well, a negative times a negative is a positive, times another negative is a negative. So I end up with a negative over a negative, which is a positive. So that is going to be my first interval. It's going to be a positive interval. The next one, I'm going to have negative 2.5 as my test point. So that means we need to think about plugging that in and what those signs would work out to be. I have a negative times negative 2.5 plus 3 is a positive. Negative 2.5 minus 2 is a negative. Over negative 2.5 plus 2, which is a negative. So I end up with a positive on the top and a negative on the bottom, which is actually negative, so that interval is a negative interval. Now, finally it gets my 0, so this will be an easier one. We'll end up with a negative times a positive times a negative over a positive. That ends up being positive over positive, which is a positive interval. So last but not least, I need to pick something on the last interval, which is 3. I'm going to choose. So again, I'm going to use my signs. That means we need to go negative times 3 plus 3 is positive. 3 minus 2 is positive. Over 3 plus 2, which is positive. So I end up with a negative over a positive, which is a negative. So for my answer, I want the ones that are less than 0, and negative numbers are less than 0. So those are the 2 intervals I want, the negative intervals. So my final solution are going to be the set of all x's from negative 3 all the way to 2, negative 2, and the interval from 2 all the way to infinity. So now we're ready to do our recap. Start by factoring everything. Then you need to make sure your inequality is related to 0. You have to use some previous rational skills to do this, because we want to sometimes add or subtract, and so you're going to need to keep in mind all of those skills you learned about adding and subtracting rationals, common denominators, and all that jazz. After you have it all set up and in the good form and related to zero, you find your critical points. And remember, your critical points are x-intercepts, vertical asymptotes, and holes. Remember that x-intercepts are okay if it's an equals to inequality. The other two are never okay because the graph doesn't exist there. Then you're going to use test points to determine the sign of the rational in each interval. Remember, I got to the point where I was just worried about signs and I wasn't even writing any numbers down, just pluses and minuses. So that's kind of a time saver if you want to use that. If you want to write it out and find all the values, that's fine by me too. Once you determine your signs, you identify the intervals that meet the inequality. So if you're looking for less than, you pick the negative. If you're looking for greater than, you pick the positive. And you write your solution using interval notation. And that's it. That's all there is to solving rational inequalities. It's basically a culmination of everything you've done before this, from simplifying rationals to graphing rationals and then applying them together.